Hi everyone, my name is Serena. I'm a volunteer with VSVS and I'm a junior at Vanderbilt studying chemistry and secondary education. And I'd love to be with you guys in your classroom today, but sadly because of the pandemic, that's not possible. So you guys are gonna have to settle for a video with me and Maya.
Hi everyone, my name is Maya and I'm currently a junior at Vanderbilt majoring in neuroscience. So today we're going to be talking about nanotechnology and magnetism. So nanotechnology and magnetism are actually really important for a lot of uses. For example, whenever we try to take precise images of satellite movements in space, we have to use ferrofluids, which is a type of nanotechnology. In addition, we use ferrofluids and nanotechnology all the time in ophthalmology when we try to treat retinal detachment. And finally, nanotechnology and magnetism is really important for cleaning up offshore oil spills. So the first thing we're going to talk about today is about magnetism. So many of you probably already know what magnets are. You've probably seen them hung up on your refrigerator. And when we were little, we probably played around with them a lot. So there are a lot of really cool components of magnets. The first is that they have both a north and a south pole. The second is that two poles that are the same will actually repel each other. So if you've heard when you're little opposites attract, this is exactly where it comes from, because in magnets, the opposite poles actually attract each other while the same poles repel. So south and south poles will repel while north and north repels as well. On the other hand, north and south poles will actually attract each other. Magnets also have an invisible force field extending around them, and these force fields actually allow attractions and repulsions to occur without the magnets actually touching. And this attraction and repulsion is actually called magnetism. We'll also learn shortly that some magnets are permanently magnetic, while others are just temporarily magnetic.
So we're going to talk a little bit about magnetism and ferrofluids as Maya has already introduced. And so first we're going to look at these bar magnets. And you've noticed that these magnets have poles and they're actually labeled. So this one's north and this one's south. And so knowing that this face of the magnet is north, I'd like you guys to guess which pole this is when you observe the following. So you notice that these two attract, so they stick together. And so since this is the North Pole, you know that this has to be the South Pole because opposite poles are going to attract. And so when you have the two North Poles together, I'd like you guys to guess what's going to happen. So that's right, they're going to actually repel instead of attract because the same poles always repel. And so I'd like you guys to also look at these disc magnets. They're pretty similar to these bar magnets, just in a different shape. And so when you look at these disc magnets, each face is going to be the opposite pole, which is why they're clicking together, right? However, when you turn it so that like one of the poles is facing the same pole, you see that one of the discs is going to actually repel, as you can see here.
So now we're going to test and see if paper clips are magnetic. So I have two paper clips here, and when I stick them together, they're not really magnetic, but I can actually make them magnetic. So I've got my wand magnet here, and I'm going to stick my paper clip on. So notice how it's actually magnetic. And the reason is because paper clips are actually ferromagnetic, and that means that they're made out of one of three different types of metals: iron, cobalt, or nickel. And these are actually attracted to magnets, even if they're not magnetic in themselves. So I've got this, and now I'm going to try to stick on other paper clips and see if it's actually magnetic. So notice how I can actually stick on the paper clips, and that means that these paper clips are now magnetic and they can be stuck to each other. So I'm going to keep doing that and see how many I can get. So I got 3 right now. And now what I want you to do is actually take off your paper clips from your magnet and try to stick on another paper clip and see if it works. So I can feel that there's slight magnetism, but it doesn't quite stick. And that's because of something called an induced magnet. So the way that we made our paper clips magnetic is through something called induction. And that's how we were able to hang all of our paper clips together. However, once I removed it, my paper clips became no longer magnetic because there's something called a temporary magnet. So our wand magnet is our permanent magnet, which means that it's always going to be magnetic no matter what. So I can stick as many paper clips on, stick it to anything magnetic, and it'll always be magnetic. However, our paper clips are not always magnetic, but we can actually induce a magnet and make it temporarily magnetic. They become magnetized in a strong magnetic field, but then they quickly lose the magnetism when the field is removed. So our wand magnet was strong enough to magnetize the paper clips by aligning the dipoles or tiny magnets within the paper clip, as you can see in the image that we have on the screen. So they'll remain aligned for a short period of time until they're jolted, and then eventually they're no longer going to be magnetic anymore.
I'd like you guys to look at this little petri dish of iron filings. And so it's just like a little dish with those tiny, tiny little iron powder. And so if you move this permanent magnet, the wand, or the bar magnet below this petri dish, you can see these little lines forming. And so there's little spikes. I hope you guys can see this. And so iron filings can actually be used to study the pattern formed by the lines of force in the magnetic field around a magnet. And so these iron filings are actually magnetized by induction, and they organize themselves into tiny, tiny, tiny little magnets that point north and south. And so it's really hard to imagine just because these are so tiny compared to these bar magnets, but they all have those two poles. And so, as I mentioned a little bit before, there's a magnetic field coming out of these bar magnets because these are permanent magnets. And so that's just a type of force that comes out of magnets. And so these patterns, this force will cause those patterns called lines of force. And so if you're looking at the lodestone, you can also see that this is a permanent magnet as well. And it's really hard because this is a weaker magnet than the bar magnets. So you can't always see these lines of force very well. But these do form lines of force as well, since the lodestone is a permanent magnet. But let's look at when the vial of iron oxide, which is just the iron oxide in some liquid, is placed beneath the petri dish. So nothing is happening, the powder is not moving or anything, there are no lines of force. And this is because the iron oxide is actually not a permanent magnet, and so it's not gonna have that magnetic force coming up from it. And so when you think about which items are permanent magnets and which are temporary, you know that the wand magnet and the lodestone are permanent magnets because they can induce a magnetic field. Whereas the iron filings, the paper clips, and the iron oxide powder in the vial, they're all temporary magnets.
So now we're going to look at a 3D magnetic field generator. So in this jar, there's a bunch of iron filings like the ones that we just saw in the petri dish. So I'm going to open the lid, and we have a bar magnet here, which is permanently magnetic. It's very similar to our wand magnet. And now I'm going to place it inside of the jar, and let's see what happens. So I'm going to move the iron filings around a little bit, and you should be able to see that you can actually see the magnetic field lines forming. So all of them are clumped up now inside of here, and these spikes mean that the iron filings are attracted to the magnet, and the accumulation of these iron filings follow the magnetic lines in 3 dimensions. So here we can actually see our magnetic field. So now we're going to talk about nanotechnology. I want you to think about a time you've seen a liquid that was magnetic. So for me, none really come to mind, and that's because it's impossible to magnetize a fluid since the liquid molecules have a lot of freedom to move around. However, with nanotechnology, we've been able to take advantage of special properties at the nanoscale to create new materials and devices. And one of those is something called ferrofluid. So ferrofluid is this bottom black material right here that you can see, and it's actually a unique material because it acts like a magnetic solid and a liquid at the same time. So we're going to be exploring some properties of our ferrofluid. What is nanotechnology? So nanoscience or nanotechnology is focusing on things that are really, really small, measured in nanometers, including things like atoms and molecules. In the field of nanotechnology, scientists and engineers make new materials and tiny devices. So we're going to explore how small a nanometer truly is. So here I have a worksheet, and as you can see, I have a ruler here and some measurements in nanometers. So I'm going to try to measure my hand and see how long it is. So if I put my hand up, it hits 16 centimeters, which means it's 160 million nanometers long, which is a huge number. And that's because nanometer is a billionth of a meter, which means it's really, really tiny. Nanometers are used to measure things that are too small to see. So a person who is a little bit over 3 feet tall is 1 billion nanometers, while a person who is 6 feet tall is nearly 2 billion nanometers. So now I'm going to show you guys some examples of some scales. There are 3 different scales that we see objects on. The first is the macro scale, or things that we see with our own eyes. The second is the micro scale, which is things that we need things like microscopes to see. And finally, we have our nanoscale objects, which we can't even see with our own eyes. We actually need special tools. Not even microscopes are able to look at these. So some examples of things on the macro scale include like trees, human beings, and butterflies that we can see every day. And then some examples of things on the micro scale include like red blood cells that we can see using a microscope. And finally, things that we can see in the nanoscale include some of these molecules, for example, like DNA, that we can actually see if we have a special tool for that. So why is nanoscience important? It's because nanoscience is changing products that we use in our everyday life, like sunscreen, household appliances, tennis balls, paints, video game consoles, and bandages, and it's just making everything more efficient and more usable.
And so the next thing I'd like to look at is this vial of ferrofluid, and then this vial of iron oxide that you've already seen before, which is in liquid. And so we're also going to use these wand magnets again, and I'd like you guys to kind of look at these properties of these two vials. And so if I have this vial held horizontally, I'd like you guys to observe what's going to happen. So I hope you guys can see that the black liquid is going to move a little bit, right? And so there's actually like powder within that liquid that is just moving. And very similarly, if you look at this powder, it's also moving along with the magnet. And you can see those little spikes that you saw before due to those lines of force. And so the ferrofluid is going to form little spikes, whereas the liquid is just going to kind of move around with the vial as the magnet moves around too. And so the further you go away, though, from this powder, the less these lines of force are going to be pronounced. And so when you're far enough away, these spikes aren't really spikes anymore, and they kind of just fall back into its normal position. And that's because when this is like super far away, the gravity kind of takes over, and the magnetic force just isn't as strong because the magnetic force is going to depend on distance. And so I'd like you guys to also think about the differences between the liquid with the iron oxide powder and the ferrofluid. And so in both, something in the vial is actually attracted to the magnet, but in the vial with iron oxide and liquid, some of the solid actually doesn't move as much, as you can see. A little bit moves, but not all of it. And then whereas in this ferrofluid, there's a lot more movement. And that's because the iron oxide is just going to clump a lot more than the ferrofluid. And the magnetite particles in the ferrofluid don't clump together because of the smaller size of the particles and because something called a surfactant has been added. And so we talked a little bit about the ferrofluid being considered nano, whereas something like the lodestone would be macro, larger in scale. And so what's considered to be very nano about the ferrofluid? It's that the size of the magnetic particles is on the nanoscale, which is like 10 times 10 to the negative 9 meters, which means it's very, very, very small, and it allows ferrofluid to have its very unique properties. And so ferrofluids actually have a ton of uses. It's used in the seals of computer hard drives, if you guys have ever had to store anything on your hard drives, and other rotating shaft motors, and also in loudspeakers to dampen those vibrations. Ferrofluids are also used in developing MRI images. If anyone's ever seen a TV show about the hospital where they have to use MRI images, and in experimental cancer treatments as well. And in the future, ferrofluids may also be used to carry medications to very specific locations of the body. So there's a ton of cool applications of ferrofluids that are coming up.